Imagine for a second the absolute, the pinnacle of professional recognition, the kind of moment that just defines a whole lifetime of work.
Hmm.
For a scientist, I mean, there's really only one peak that fits that description, right?
It's a Nobel Prize. It has to be. That phone call from Stockholm, I mean, it changes everything. It's the signal to the entire world that you haven't just done, a good job.
Yeah.
You fundamentally altered the course of human history.
Exactly. Fundamentally altered it.
Yeah.
So hold that image in your mind.
Yeah.
The confetti, the press conferences, the King of Sweden handing you a medal, just the ultimate final validation.
The victory lap.
Yes. Now, I want you to hard cut away from that.
Yeah.
Just wipe the slate completely clean.
Okay. Where are we going with this?
It's 1985. We're at a border crossing, Hungary, and it's a gray, tense scene. You can picture it. Soviet block guards, machine guns, dogs sniffing the wheel wells of the cars.
Yeah, not a friendly place.
And inside this one old Lada, there's a family. They're trying to leave the country for good. A father, a mother, and a 2-year-old girl.
And the most valuable thing in that car isn't the luggage. It's not the passports. It's not even the car itself.
No, it's a teddy bear.
A teddy bear.
A simple teddy bear sitting right there in the lap of that 2-year-old girl. Because stuffed deep inside the batting of that bear, right where a kid would squeeze it for comfort, is roughly 900 British pounds.
Which, to us today, that might not sound like a fortune. But in 1985, Hungary, behind the Iron Curtain, that was an astronomical sum of money.
Right. It was their entire life savings. They'd sold their cars, sold off their furniture. They scraped together every single forint they had.
And then exchanged it on the black market, which was incredibly risky in itself.
The stakes just couldn't be higher. I mean, if one of those border guards decides to just squeeze that bear a little too hard,
yeah,
they find that cash.
Oh, it's not a fine. It's jail time.
The career is over. The dream is dead. Everything is gone.
And that money, smuggled inside a child's stuffed animal, was essentially the seed capital for a scientific revolution.
Today, we are doing a deep dive into the story of Katalin Karikó. And you're right, usually when this story gets told, we start at the finish line. We talk about the 2023 Nobel Prize in Physiology or Medicine.
We talk about the COVID-19 vaccines that saved, literally millions of lives.
We focus on the victory lap. But our mission for this deep dive it's different. We need to look at the 40 years of, frankly, darkness that came before all the confetti. This isn't just a biography of a scientist. This is a case study in resilience. It's a story about the blindness of institutional academia and how a biological hack that was ignored, underfunded, and even mocked for decades ended up rewriting the source code of modern medicine.
It is the ultimate survivor story. And to really, truly understand the magnitude of what Karikó achieved, you have to understand just how close this technology came to never existing at all. It was on a knife's edge for decades.
So let's rewind the tape. We're not starting in some high-tech lab at UPenn or BioNTech. We're going way, way back to the source. We need to understand the environment that forged this person.
We are going to Kisuslasz, Hungary. Karikó was born on January 17, 1955. And, when we use that phrase, humble beginnings, I think we often gloss over what it really means.
Yeah, it becomes a cliche.
It does. But in post-war Hungary, in the countryside, this was a life stripped down to the absolute essentials. We're talking about a small adobe home.
Made of mud brick.
Exactly. Only one room heated in the winter, no television, no refrigerator, and the detail that always gets me, no running water.
Wow. So you're not just turning on a tap. You are physically pumping water from a well every single day.
It's a very physical, very direct existence. Her father, János, was a butcher. Her mother was a bookkeeper. So you have this really interesting mix right from the start.
How so?
Well, you've got the practical, visceral reality of biology right there in the butcher shop, and then you've got the precision of numbers and ledgers from her mother. It's the hands-on and the analytical all in one household.
But there's a shadow hanging over this family, isn't there? It wasn't just about being poor. There was a political weight.
A very heavy one. You have to remember the context. 1956, the Hungarian Revolution.
Right, against the Soviets.
It was a nationwide uprising against the government and its Soviet policies, and it was crushed, just brutally put down. And Karikó's father, János, he participated in that revolution.
And in a Soviet satellite state in the 50s and 60s, you don't just move on from participating in a revolution.
No, the state remembers. The state always remembers. He was punished for it. He lost his job for a time. So Kari grows up in this environment where, well, where authority is dangerous, she sees her own father, a strong, hard-working man, having to navigate a system that is fundamentally suspicious of him.
That has to implant a very specific kind of worldview in a child.
I think so. You learn early on that the system isn't always right. You learn that institutions can be wrong, and that sometimes you have to survive in spite of them, not because of them.
And yet, despite the lack of resources, or maybe, because she had to find entertainment in the world right around her, she becomes an academic prodigy.
She was just relentless. By primary school, she's already placing third in the entire country in biology competitions. She had this raw, unfiltered curiosity about nature. She wasn't learning biology from an iPad or a screen.
No, she was learning it from the plants in the garden and the animals in the yard.
Exactly. It was real and tangible to her.
So she excels. She eventually moves on to the University of Szeged. She gets her Bachelor of Science in '78, her PhD in '82. She lands a good job at the Biological Research Center, the BRC. On paper, she's on the perfect path.
She is. But this brings us to a part of her history that is, well, it's really complex and, frankly, pretty terrifying.
The Intel asset controversy.
That's the one.
So decades after the fact, it comes out that from 1978 to 1985, her name was listed in the files of the Communist Secret Police as an intelligence asset.
And when that news broke, it could have been a career-ending scandal.
It could have been. But we really need to parse this with extreme care because the nuance here is everything.
It is. And Karikó has been incredibly transparent about this chapter of her life. She wasn't a volunteer spy. She wasn't an informant. She was a victim of that very system we just described.
How did it happen?
The authorities approached her. They knew her father's history as a so-called counter-revolutionary. And they blackmailed her. The choice was laid out in no uncertain terms.
So it was an ultimatum.
A brutal one. Sign this recruitment paper, or your father will face severe reprisals, and your own scientific career, which you've worked so hard for, will be terminated immediately.
My God. It's a literal dead end. You sign the paper, or you lose your entire life's work and you endanger your family.
There was no choice. So she signed. But, and this is the absolute crucial part that's been corroborated by the historical records, she maintains she never acted as an active agent.
So she never informed on anyone?
Never. In intelligence terms, she was what you'd call a paper agent. She existed in a file to satisfy some bureaucrat's quota, but she never reported on her colleagues. She never provided operational information. She walked this incredible razor's edge of appearing to comply while doing absolutely nothing to harm anyone.
Imagine the psychological weight of that, though. You're in your 20s, you're trying to decode the fundamental secrets of life in the lab, and you have the secret police technically breathing down your neck.
It's a pressure cooker. It has to force you to be self-reliant. You learn you cannot trust the institution to protect you. Your survival is up to you.
And eventually that pressure cooker does explode. But what's so interesting is that it wasn't the police that finally drove her out of Hungary. It was something much more mundane, something scientists everywhere can relate to.
Funding. It almost always comes down to funding. In 1985, her lab at the BRC, it lost its funding. The money dried up.
So she had no resources to continue her research.
Zero. And for a scientist like Karikó, not doing research is like not breathing. So she starts looking abroad desperately.
She gets an offer.
She gets a job offer from Temple University in Philadelphia. It's a lifeline. And that brings us right back to that gray morning at the border crossing, the decision to just leave everything they know behind.
Let's go back to that teddy bear for a minute. It's 1985. She's with her husband, Bella Francia, and their daughter, Susan, who's just a toddler. They sell the car. They have to go to the black market to get British pounds.
Because you couldn't legally just take currency out of the country.
Right, there were strict limits. You were allowed to leave with a tiny amount of cash, maybe enough for a taxi ride, but certainly not enough to start a new life in America. So smuggling was the only option.
And if that guard had just been having a bad day, if he'd picked up the bear and felt something crinkle,
we would not be having this conversation.
It's terrifying to think about.
There would likely be no Pfizer or Moderna COVID vaccine in 2020. The course of the pandemic would have been completely different. So much history hinged on a piece of batting in a stuffed toy.
But they make it through. They land in America, the land of opportunity.
Or so the brochure says. But the reality for an immigrant, even a brilliant PhD scientist, is often a lot grittier than that. She starts her postdoctoral work at Temple University.
And to be fair, scientifically, this was actually a pretty exciting time for her. She wasn't just, washing test tubes in a corner.
No, she was right in the thick of it. This is the mid-'80s. She's participating in clinical trials using something called double-stranded RNA or dsRNA.
And they were investigating treatments for HIV/AIDS and chronic fatigue syndrome. This was cutting-edge stuff at the time.
So what was the mechanism? What were they actually trying to do with this RNA?
They were studying something called interferon induction.
Okay, let's break that down for the listener. Interferon, what is it?
Think of interferon as the body's. It's citywide air raid siren. When a cell detects a viral invader, it starts pumping out these proteins, interferons, to tell all the neighboring cells, shields up, there is an intruder, stop replicating now.
Okay, so it's an alarm system.
A very powerful one. And Karikó was working on using RNA to artificially trigger that siren to sort of preemptively boost the immune system's defense against viruses.
That sounds incredibly promising, groundbreaking even for the 80s.
Well, it was. The science was fascinating. But the workplace dynamic, that was an absolute disaster. She was working for a man named Robert J. Suhadolnik.
And this relationship turns into a complete nightmare.
It really does. Look, the mentor-mentee relationship in academia is incredibly powerful. Your mentor, your PI, they hold the keys to your visa, your funding, your reputation, everything.
It's a huge power imbalance.
Huge one. And in 1988, Karikó received a job offer from Johns Hopkins University.
Which is the big leagues. I mean, that's the Ivy League of medicine. A massive step up.
A huge step up. But she made a tactical error. And maybe it was out of excitement or maybe just naivety about the cutthroat nature of academic politics. She accepted the offer from Hopkins before she told Suhadolnik she was leaving.
Oof. And he didn't take it well.
He took it as a personal betrayal, and his reaction was, it was vindictive on a level that is just hard to comprehend.
What did he do?
Because Karikó was a foreign national, her visa status was tied directly to her employment at Temple. Suhadolnik knew this. And he threatened her with deportation.
He actually played the deportation card on a scientist in his own lab.
He went even further. He contacted the U.S. immigration authorities himself and reported her, claiming she was in the U.S. illegally or that she was violating her visa status.
That is just astonishing. You have a brilliant scientist trying to advance her career, and her boss calls immigration on her because his ego is bruised.
And it worked, at least in the short term. Johns Hopkins got spooked and withdrew the offer. They didn't want to deal with the legal mess.
So she's stuck.
She's in legal limbo. She had to fight an extradition order. She's facing the very real possibility of being sent back to Hungary, where she now has no job and has burned bridges by leaving in the first place.
She did fight it, though.
She did. She won the legal battle eventually. But Suhadolnik didn't stop there. He started bad-mouthing her to other institutions. In the small, insular world of academic research, a bad reference from your principal investigator is the kiss of death. She was effectively blacklisted.
I think most people would have quit.
Uh-huh.
I honestly think I would have quit at that point.
Mm-hmm.
Okay, America doesn't want me. My boss is actively sabotaging me. I'm going home.
And it really speaks to that iron-willed resilience we talked about, forged back in Hungary. She didn't quit. She found a temporary refuge at the Uniformed Services University of the Health Sciences in Bethesda.
A bridge job.
Exactly. It kept her in the country, kept her working with signal protein interferons again. But the real story, the one that leads to the Nobel Prize, that begins when she finally lands a position at the University of Pennsylvania in 1989.
UPenn. This is the chapter I always think of as the wilderness.
That's a good way to put it.
She gets hired to work with a cardiologist named Elliot Barnathan. And this is where she decides to bet her entire career, everything she has, on messenger RNA.
Which to us, sitting here today, having had an mRNA vaccine shot into our arms, sounds like a great bet, a brilliant move.
Of course.
But we have to contextualize this. In 1989, betting your career on mRNA was considered scientific suicide.
Why? What was the reputation of the molecule back then?
It was a scientific backwater, a dead end. To understand why, you have to look at the central dogma of biology. DNA makes RNA, and RNA makes protein.
Right.
DNA is the hard drive. It's stable, it's permanent, it holds the master blueprints. Protein is the product. It's the muscle, the enzyme, the thing that does the work.
And mRNA is just the messenger.
It's just the memo. It's the sticky note that carries the instruction from the hard drive in the nucleus to the protein factory in the cytoplasm.
And sticky notes are fragile. They're temporary.
Extremely. mRNA is designed to be transient. The cell is supposed to read it and then destroy it immediately. In the lab, if you even look at it wrong, it degrades. It just turns into mush. On top of all that, making synthetic mRNA was prohibitively expensive.
So the scientific consensus at the time was, you can't make a drug out of this stuff. It's too unstable, too expensive, and the body will just chew it up. It's a dead end.
100%. all the money, all the excitement was around DNA gene therapy, the idea of going in and fixing the hard drive permanently. But Karikó saw the danger in that.
What danger?
If you edit the DNA, you change the code forever. If you make a mistake, it's a permanent mistake. It's passed down to every new cell.
But with mRNA?
It's a software patch. It's temporary. Her vision was, what if we don't need to permanently change a patient's genetics? What if we just send in a temporary instruction? Hey, body, make this specific protein for a few days to heal this wound or fight this virus or replace this missing enzyme.
You're turning the patient's own body into the drug factory.
Precisely. It's a brilliant, elegant concept. But in the 90s, nobody wanted to fund a skyscraper built out of wet tissue paper.
So she wrote grants.
Constantly, she submitted grant after grant after grant. I want to use mRNA to treat cystic fibrosis. Rejected. I want to use mRNA to treat stroke. Rejected.
And in academia, grants are oxygen.
They are. If you don't bring in money, you are seen as a liability to the university. You're taking up space.
And this leads us to 1995. The year of the demotion.
This is a pivotal and I think incredibly painful moment in her story. Karikó was on the tenure track. She was working toward becoming a full professor. That means job security, respect, your own lab, the whole thing.
It's a dream.
The academic dream. But because she could not get funding for her crazy mRNA ideas, UPenn gave her an ultimatum.
They didn't just deny her tenure, they demoted her.
They knocked her down from the tenure track, they cut her salary. They essentially told her, you are no longer a professor in waiting, you are now just a senior research associate. This mRNA thing is a hobby, not a career path.
That is just, it's so humiliating. You're a PhD, you've been working for decades, and your employer basically tells you that you've failed.
Professionally devastating. And her working conditions reflected that status change. She wasn't working in some gleaming, well-funded institute. She was often relegated to the edges, relying on the kindness of other researchers like Barnathan and later David Langer to just give her some bench space. Can I work in this corner of your lab?
So why did she stay? I keep coming back to this. Why stay at an institution that so clearly didn't value her or her work?
Because she believed the science was true. It's as simple and as complicated as that. She knew that if she could just solve the stability and the inflammation problem, the potential was limitless. She couldn't walk away from the puzzle.
And then after all this struggle, serendipity strikes. And it strikes in the most mundane place imaginable.
The photocopier.
I love this part of the story. It's 1997. She's standing at the copy machine at UPenn, probably copying yet another rejection letter or some journal articles, and she just starts chatting with the new guy.
Drew Weissman. He had just arrived at UPenn from the National Institutes of Health, the NIH. He was an immunologist, a vaccine guy. And he was frustrated because he was looking for a new way to develop an HIV vaccine, but all the old methods were too slow and ineffective.
So you have this collision. Karikó, the obsessive biochemist who can make any RNA you want, but has zero money and zero institutional respect.
And Weissman, the respected immunologist who has startup funding from his new position but needs a new technology platform.
He was the missing piece for both of them.
A perfect marriage of skills. They started talking. Karikó basically told him, I can make any RNA you want. Weissman was intrigued. He decided to use some of his startup money to fund her work, and they formed a partnership.
Peanut butter and jelly.
Exactly. But let's be really clear here. Just because they teamed up didn't mean it started working right away. They immediately ran into a massive biological brick wall.
The inflammation problem.
This was the hurdle that had stopped everyone else in the field dead in their tracks. When Karikó made the synthetic mRNA in the test tube and they injected it into mice, the mice didn't just make the protein, they got really, really sick.
Sick how? What did it look like?
They looked like they had a massive viral infection. Their fur ruffled up, they became lethargic, they stopped eating and moving. Their immune systems were launching an all-out attack on the mRNA.
So the body looked at this synthetic message and said, intruder, red alert, kill it.
Right. Our bodies have these ancient sensors. They're called toll-like receptors. They're the sentries at the gate. Their entire job is to patrol for foreign-looking genetic material like the RNA from a virus.
Okay.
When they saw Karikó's synthetic mRNA, they pulled the fire alarm. This triggered a huge cascade that not only destroyed the mRNA, but also caused massive systemic inflammation.
So it's game over. You can't have a medicine that makes the patient sick, and on top of that, gets destroyed before it can even do its job.
Most scientists would have stopped there. They would have said, okay, the critics were right all along, it's toxic, it doesn't work. But this is where Karikó's detective brain kicks in. She did something brilliant. She looked closely at her control group.
What was the control?
She was using transfer RNA, or tRNA, as a comparison. tRNA is a natural form of RNA that's abundant in all of our cells. And she noticed something crucial. When she injected the natural tRNA, the mice didn't get sick. The toll-like receptors didn't fire. The alarm stayed silent.
So the body was totally cool with the natural tRNA, but it hated her synthetic mRNA. So why? What was the difference?
That was a billion-dollar question. She looked at the chemistry. RNA is built from 4 letters, 4 nucleosides. A, C, G, and U stands for uridine.
Okay, A, C, G, U.
Got it. Through a series of painstaking experiments, she and Weissman figured out that the toll-like receptors were specifically reacting to the uridine. The U was the red flag that was giving away the intruder.
Well, wait, tRNA has uridine in it too, doesn't it?
It does. But here's the aha moment. In natural tRNA, the uridine is often chemically modified. It wears a disguise. One of the most common of those modifications is called pseudouridine.
Pseudouridine, okay.
It's basically uridine that's been sort of rotated slightly at the molecular level. It's the same number of atoms, but it's arranged in a different shape. And Karikó's hypothesis was, what if the immune system is blind to this specific shape? What if I replace the normal uridine in my synthetic mRNA with this modified pseudouridine?
It's like putting a fake mustache and glasses on the intruder so the bouncer lets them right into the club.
A molecular mustache. That's a perfect analogy. Yes. So they went back to the lab. It was tedious, painstaking work. They had to synthesize new strands of mRNA where every single U was swapped out for pseudouridine.
What happened?
They injected it into the mice. They waited. And the mice were fine.
No sickness?
No fur ruffling, no lethargy, no sickness at all. And crucially, when they checked, the cells were pumping out the desired protein in massive quantities, way more than before.
It worked?
It worked. The immune system completely ignored the message, but the cell's protein-making factories read it perfectly. This was the breakthrough. This was it. They had turned a toxic, inflammatory molecule into a stealthy, potent medicine.
That is the eureka moment. That is the moment the world changed, even if the world didn't have a clue yet.
They were ecstatic. They wrote up the paper. This was going to be huge. They sent it to Nature.
And Nature immediately cleared the front page for them.
Nature rejected it within 24 hours, didn't even send it out for full review,
Well,
so they sent it to Science. Science rejected it too.
But why? How could they not see the importance of this?
Because in the grand scheme of science at the time, it seemed niche. It was a paper on RNA modification. It seemed like a minor biochemical curiosity, not a medical revolution. The reviewers, the editors, they just didn't grasp the enormous implication that this single change solved the fundamental barrier to mRNA therapeutics.
So it did get published eventually, though.
Yes, it found a home in the journal Immunity in 2005, a very respectable journal, but not one of the absolute top-tier blockbusters. And even after it was published, crickets.
Nothing.
Karikó has said she expected her phone to start ringing off the hook. It didn't ring once.
That is just... It's heartbreaking. You solved the puzzle that stumped everyone for decades, and nobody cares.
But they kept going. They knew what they had. They now had the core technology, the nucleoside-modified mRNA. They filed for patents. And this brings us to the commercialization phase, which involves what I honestly think is one of the biggest business blunders in the history of university tech transfer.
The UPenn blunder.
Absolutely. So Karikó and Weissman had founded a small company, RNRX, but under university rules, UPenn owned the intellectual property, the patents.
Okay, that's standard.
It is. And UPenn's tech transfer office looked at these patents for this weird modified RNA, and they said,
We don't see much value here.
Exactly. They shopped the license around. Nobody from Big Pharma was interested. So UPenn decided to just cut their losses. They sold the exclusive license to the patent to a small lab supply company in Wisconsin called CellScript.
A lab supply company, not a biotech firm.
No, a company that sells reagents to other scientists. It was run by a guy named Gary Dahl, who, to his credit, saw the value for research tools. But UPenn sold the rights for a relatively tiny amount. Reports say it was around $300,000.
They sold the golden goose for the price of a mid-range suburban house.
And here's the gut-punching twist. A few years later, a venture capital firm called Flagship Pioneering, which was backing this hot new startup called Moderna, they came calling. They contacted Karikó directly. They said, we've read your 2005 paper. We think this is the future. We want to license this technology.
And she had to tell them.
She had to say, I'm sorry, I can't help you. It's not available. The university that demoted me also sold the rights to my life's work to a guy in Wisconsin.
Oh, that phone call must have been excruciating. Just imagine that.
It forced Moderna and later a German company called BioNTech to go to CellScript and pay millions upon millions in sub-licensing fees. UPenn missed out on what would have become a multi-billion-dollar royalty stream.
And this had to be the final straw for Karikó at UPenn.
The writing was on the wall. She realized she was never going to get the respect or support she deserved there. So in 2013, BioNTech, which was a small German startup at the time, but one founded on the promise of mRNA, offered her a job.
And not just any job.
No, they offered her a vice presidency. They understood the technology. They valued her. They saw her as a pioneer, not a problem.
So she leaves. She finally moves to Germany.
She commuted, actually, for a long time, living out of a suitcase again. But she was finally in an environment that got it. They promoted her to senior VP by 2019. She was home.
Now, before we get to the pandemic, there's one last crucial piece of the puzzle we need to put on the board. We have the mRNA, the message, we have the pseudodyne, the molecular disguise, but we still need a delivery truck.
Correct. You can't just inject naked mRNA into the bloodstream. There are enzymes in our body called RNases that are designed to do one thing: find and destroy free-floating RNA. Your message would be eaten up in seconds. It needs armor.
And that armor is the lipid nanoparticle.
The LNP. Basically, tiny little balls of fat. Karikó had actually collaborated on this problem with a scientist named Ian McLaughlin at a company called Techmira way back in 2006.
So this wasn't a new idea either.
No, the work on delivery systems was happening in parallel. The idea is to encapsulate the fragile mRNA inside this lipid shell. The LNP protects its precious cargo as it travels through the body. Then, when it reaches a cell, its fatty outer layer fuses with the fatty cell membrane, and it releases the mRNA inside.
It's like a microscopic Trojan horse made of soap bubbles.
That's a great way to think about it. So by the end of 2019, all the pieces are finally on the board. You have the modified non-inflammatory RNA, you have the LNP delivery system, and you have two companies, BioNTech and Moderna, that have spent years figuring out how to manufacture the stuff at scale.
It was a loaded gun, just waiting for a target.
And in January of 2020, the target appeared. A novel coronavirus emerging out of Wuhan, China.
The world panicked. I rember it vividly. Governments shut down, economies ground to a halt. But inside BioNTech and Moderna, there wasn't panic. There was a sprint.
Right. Because they had this platform technology, they didn't have to invent a vaccine from scratch.
This is the part I think so many people misunderstood during the pandemic. I remember hearing it constantly. Oh, it was rushed. Vaccines take 10 years to develop. How did they do this in 10 months?
It's the biggest misconception of the whole crisis. It didn't take 10 months. It took 10 months plus the 25 years of Karikó and Weissman struggling in the dark, being rejected and demoted.
They just had to plug the new code in.
That's it. As soon as the genetic sequence of the SARS-CoV-2 virus was published online, they just took the genetic code for the spike protein, pasted it into their existing mRNA template, and hit print. Udur Shahin at BioNTech designed their vaccine in a single weekend.
Oh, shit.
The rest of the time was spent on manufacturing scale-up and the necessary clinical trials to prove safety and efficacy. But the core science, the invention, that was ready because of those decades of rejection and persistence.
And the result was just.
Yeah.
It was spectacular. Over 90% efficacy against the original strain.
It saved millions of lives. It allowed society to reopen. It is arguably the greatest medical and manufacturing feat of the 21st century.
And finally, the world caught up to Katalin Karikó.
The avalanche of awards. It was surreal to watch it happen in real time. She went from being a completely unknown scientist to being on the cover of magazines, Time Magazine's Hero of the Year.
The Lasker Award, which they call the American Nobel, the Tang Prize, and then the big one.
October 2nd, 2023, the Nobel Prize in Physiology or Medicine, the Summit.
I love her reaction to it. She didn't give some big ego-driven speech. Her quote was something like, "I dreamt about doing research, not getting an award."
It's so consistent with her entire story. She is a solver of puzzles. She was never in it for the fame or the money. She was in it because she was obsessed with a question and wanted to find the answer.
So let's bring the story up to the present moment. We're recording this in January of 2026. A little over 2 years have passed since the Nobel. What has she been up to?
Well, she certainly hasn't retired to a beach somewhere. In October 2023, just after the prize was announced, she published her autobiography, Breaking Through: My Life in Science.
Which is a fantastic and very fitting title.
It is. It became an instant bestseller in Hungary. By 2025, it had been translated into 9 different languages. It won the Libri Literary Prize in 2024 and the Asimov Prize in May of 2025. It's really becoming a canonical text for young scientists, a story of persistence.
And she did something really special with the prize money, didn't she?
She did. You know, the Nobel comes with a significant cash award, over $1 million. In April of 2024, she donated more than $500,000 of that money right back to her alma mater, the University of Sigyd.
The place where it all started. Full circle.
Giving back to the institution that educated her, making sure the next generation has resources and opportunities that she didn't have. And speaking of full circles, in November of 2024, she returned to Temple University.
The scene of the crime.
Exactly. The scene of the deportation threat. She went back to that campus, not as a vulnerable immigrant postdoc, but as a Nobel laureate to give a lecture.
Wow. That must have been an incredibly powerful moment. A definitive, quiet vindication.
And the accolades kept coming. In May 2025, she was elected to the U.S. National Academy of Sciences, which is one of the highest honors for an American scientist.
So what's her status now? Is she still at BioNTech?
She left her executive role at BioNTech in 2022, even before the Nobel, to devote more time to pure research. She's currently a professor at Szeged, and in the ultimate irony, she's also affiliated with UPenn, who now celebrate her as one of their greatest luminaries.
Funny how that works. Once you win the Nobel, the university that demoted you and sold your patent for pennies suddenly puts your face on the front of the brochure.
Success has many fathers. Failure is an orphan.
We have to mention one other person in this story before we look to the future. Her daughter, Susan Francia.
The little girl with the teddy bear full of cash.
She didn't do too badly for herself either.
No, not at all. Susan grew up watching her mother's relentless 7-days-a-week work ethic. She clearly absorbed that intensity. Susan Francia went on to become a 2-time Olympic gold medalist in rowing for Team USA.
That is just an insane family stat sheet. Mom has a Nobel Prize in medicine. Daughter has 2 Olympic gold medals.
It really speaks to a certain genetic or maybe environmental drive, a capacity for enduring pain and discomfort for a distant goal, whether it's rowing a boat until your lungs burn or pipetting clear liquids until your eyes blur. They simply do not know how to quit.
So what does all of this mean for us now? We have the COVID vaccine. It's part of our lives. But I've heard you say before that calling this vaccine technology is like calling the internet email technology. It's way too small a description.
It is so much bigger than just vaccines. We need to stop thinking of mRNA as just for infectious diseases. We need to think of it as a drug platform, a new way of making medicine.
Explain that shift in thinking.
Okay, think about most drugs today. If you're a diabetic, you inject insulin. Insulin is a protein. To get that insulin, we have to build these massive billion-dollar factories to grow the protein in giant vats of bacteria, then purify it, bottle it, and keep it cold all the way to the patient.
It's a complex, expensive industrial process.
It is. Karikó's technology completely flips that model on its head. Instead of making the protein in a factory, we just write the instruction code, the mRNA for that protein. We package it in an LNP, we inject the code, and the patient's own cells become the factory.
So you can make the body manufacture its own medicine on demand.
Exactly. This opens the door to something called protein replacement therapy. Think of genetic diseases like hemophilia or cystic fibrosis, where the body is missing one specific crucial protein. We can just send the email with the blueprints, and for a short time, the body can make what it's missing and fix itself.
What about cancer? That's the one everyone always asks about.
That's the holy grail, immuno-oncology. The idea is that we can take a biopsy of a patient's specific tumor, sequence its DNA, find the unique mutations that make it different from healthy cells, and then create a custom mRNA vaccine that teaches that patient's immune system to recognize and hunt down only those cancer cells wherever they are in the body. It's truly personalized medicine, made to order.
Heart disease.
They're already working on it. Injecting mRNA directly into the heart muscle after a heart attack, a condition called ischemia, to tell the cells to grow new blood vessels and heal the damaged tissue.
It honestly sounds like science fiction.
It's rapidly becoming science fact. We're also looking at using mRNA to temporarily express proteins that can reprogram cells to generate pluripotent stem cells, basically rebooting older cells to a younger, more flexible state. The horizon is it's limitless. This is a new branch of medicine, comparable to the discovery of antibiotics or the invention of recombinant DNA.
And it all goes back to that basement lab, to that demotion, to that one scientist who wouldn't give up.
It does.
As we wrap up this deep dive, I want to leave our listeners with one final, maybe provocative thought. We celebrate Katalin Karikó today. And we should. She's a hero. She has a household name in science. But
we have to talk about survivor bias.
exactly. We know her story because she made it.
She survived. She survived the secret police in Hungary. She survived the deportation threats at Temple. She survived the constant grant rejections, the demotion, the lack of funding at UPenn. But you have to ask yourself, how many other Karikós were there?
That is a haunting question.
How many brilliant scientists were there in the 90s or the 2000s who had an idea that was just as big, just as revolutionary as mRNA, but they got demoted and they couldn't take the financial hit and had to leave science, or their boss threatened them and they just went home, or they got rejected by Nature and Science 3 times in a row and just decided, well, I guess I'm wrong.
And those ideas, those potential cures, they just died in a trash can.
Exactly. We will never know what we missed, what cures we don't have today, because our academic system is fundamentally designed to fund the consensus, not the outliers. The system loves the safe bet. It is terrible at recognizing the kind of genius that, at first glance, looks like a mistake.
And for decades, Katalin Karikó looked like a mistake to them.
For 40 years, she looked like a failure to the scientific establishment.
I want to leave you with that final image. Not the Nobel ceremony in Stockholm, not all the applause. I want you to picture a woman in her 40s. She has just been demoted by her university. She is working in a cramped, borrowed corner of a lab. She is transferring clear, invisible liquid from one plastic tube to another. She has no funding. Her bosses think she is wasting her time. But she keeps working. She holds the key to saving the world in her hands. She just doesn't know that the applause is still 20 years away.
He just keeps working.
She just keeps working. That's the lesson. That is the legacy of Katalin Karikó. So, to all our listeners, look for the outliers in your own field. The people who are stubbornly, obsessively working on something that everyone else thinks is weird or a waste of time. They might just be onto something big.
Thanks for listening to The Deep Dive.
Thank you.